Okay, so who first proposed the idea of the atom? Democritus. Okay, Democritus was the first atomist. Okay, but it wasn't widely accepted. Okay, like took another 2,000 years for people to kind of believe that it might be possible. Why was his idea not acceptable?
Because he wasn't the most respected thinker. Aristotle was more respected, and he had a different idea.
Okay, there were other more respected thinkers who had different ideas. Okay, what else? Yeah, there was no proof. He was asking him to believe in invisible particles. Okay, and why was that not as good? Was there something else that was better? Right, they believed in the four elements, and the four elements was something they understood. It made sense. They could see it. Okay, like the mixtures, like we talked about, how steam is a mixture of fire, water, and air. Okay, that kind of thing made sense to them, and so that model was more acceptable. Okay, it seemed to have more evidence to support it than imaginary particles. Okay, so his idea just kind of fell by the wayside. Okay, question number 2. What element did the Greeks believe all matter was made of? Well, we just talked about that. It's earth, air, fire, and water. Okay, those are the 4 elements. Okay, that was a logical conclusion because, as we said just a minute ago, it made sense. They had, they could make up mixtures for everything that they encountered, and so that kind of thing just was more reasonable and more logical. Okay, they had a system in place that applied these 4 elements. Okay, so they went with that. And that's really what we do with everything. Okay, if we have something that makes sense and it's a good system, then we keep it. Okay, number 3. During the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. The alchemists. All right, so the alchemists were this group of people, and what were they trying to do? Right, they were trying to turn cheap substances into gold, basically, transmute stuff and basically do things that we know now and are not physically possible. Okay, but that's what they were trying to do. Then they ended up mixing lots of things together and observing a lot of things about the physical and chemical properties of matter. Okay. All right, number 4. In the late 1700s, a man used data from many experiments on matter to develop an idea on the structure of matter. Who was he, and what were the points of his theory? Okay.
And he believed that all atoms were simple spheres, and that his theory stated that they were all identical elements of atoms of different elements could combine.
Right.
Chemical reactions would occur, but it wouldn't change the elements, and all elements were made of them.
Right. Okay, so before we were so rudely interrupted, we had a really good thing going here about Dalton and the 4 points of his atomic theory. So obviously it was Dalton was the person, John Dalton. Okay, points of his atomic theory. All matter is made up of tiny indivisible particles called atoms. That was the first point, so he resurrected Democritus's idea. Second point, okay, atoms of all of the same element are the same. Okay, so all oxygen atoms are the same. Okay, all atoms of carbon are the same. For all intents and purposes, we still know that to be, at least for the most part, true. Okay, third point, okay, atoms can combine with each other in simple whole number ratios to make compounds. The whole number part is important. Okay, so when compounds are made, there's never a half an atom, all right, or a quarter of an atom or something like that. And the last point is, what happens in a chemical reaction? Atoms can be separated, they can be joined, they can be rearranged, but they can't be... Switch on my new case, it's not very good. It always keeps coming off. Okay, they can't be essentially changed into something else. All right, I can rearrange stuff, I can make things that appear like they're different from what I started with, but I still have the same atoms that I started with. They may just be in a different combination. So if I start out with sodium and chlorine, I'm not suddenly going to end up with lead on the other side. Okay, I can't create a new atom. I can just change the combinations and permutations of whatever I have. All right. Everybody kind of follow there? All right, so those are the 4 points. And like we said, that's something that could easily be a quiz question or a multiple choice question on an exam. Okay, number 5. Okay, looking at this theory, what things do you now know that can prove some of his ideas wrong? Right, okay. First thing is that we know that there are isotopes, things called isotopes. And isotopes are slightly different versions of an atom. Okay, now, isotopes are only different in one way. and that is that they have a different number of neutrons than most of the atoms of that element. Okay, so if we're looking at, and I think the example we used the other day was carbon-14. Okay, carbon-14 is used in what we call carbon dating. Has anyone ever heard that? Okay, carbon dating is what we use to determine the age of basically man-made artifacts and things like that. Okay, we can use it because carbon-14 has extra neutrons in the nucleus of the atom, more than a normal carbon atom would have. And as a result, it's a little bit unstable and it breaks down. Those neutrons actually come off. It's slightly radioactive. So what we can do is we can look at what a brand new thing, how much of it would have, or sorry, how much of this brand new thing would have carbon-14, okay, or how much carbon-14 would be in this brand new thing, okay, and then 100 years down the road, how much carbon-14 would be left, okay. From that, we can determine, because it breaks down at a very predictable rate, how old something is, right? So carbon-14 is an isotope of carbon. Normal carbon, okay, normal carbon has 6 protons and 6 neutrons and 6 electrons. Carbon-14 has 6 protons, 6 electrons, but 8 neutrons. Okay? So it's slightly different. The most important particle, the protons, is always the same number. In every isotope, the number of protons is the same. It's always what's the atomic number. Okay, so that's important to realize. But there are isotopes out there, so not every atom of an element is identical, but like 98% of them. Okay, sometimes it's even more than that. Okay, only a very small percentage of any given element would be a different isotope. Everybody all right with that? Okay, any other thing that we know of now that might be kind of not right?
You said the atoms were indivisible, but there's going to be atoms.
Right, we can split certain atoms. Okay, so we know that at least from a purely technological standpoint, yeah, we can split atoms. Okay, do all atoms split? No, they don't. Okay, but for all intents and purposes, an atom is indivisible. It doesn't. There's only a few that really kind of break down on their own. Okay, uranium, kind of big atoms like that might do that, but for the most part, okay, atoms are truly indivisible. Okay, we don't break them on a regular basis. Right, that actually wasn't part of his atomic theory. That was just his model. But yes, yeah, we know that obviously his solid sphere model is no longer acceptable either. Okay.
We found that things that atoms can change based on nuclear fission or fusion.
Right, so the nuclear process can change an atom. Yeah, any nuclear process can change an atom. Well, obviously, that came after Dalton. Okay, so fission would be the splitting of the atom. Fusion, which actually occurs in nature, okay, is a process where atoms are forced together. Okay, fusion is the source of power for the sun. The immense gravity of the sun pulls 3 hydrogen atoms together and makes a helium atom. Okay, in the process, that releases a large amount of energy. So there are nuclear processes that do go on. Okay, but for the most part, again, atoms are indivisible. Okay, fusion's not really considered part of that because it's not dividing an atom; it's actually forcing many of them together. All right, so the models of the atom that we discussed, okay, obviously we started out with the solid sphere model. Okay, that was Dalton's idea, and it was really just a blind guess. He had no idea what they looked like, and none of his experiments really talked about or showed that they could be anything other than that. So it was acceptable for quite a while. Okay, then Thomson comes along, J.J. Thomson comes along, and he discovers that there are moving negative charges that can move around in a chemical reaction. Dalton's solid sphere model does not explain that. So he comes up with the plum pudding model, solid sphere with electrons embedded in the surface that can fall off in a reaction. Okay, shortly thereafter, okay, we got Chadwick who discovers, we discover protons, Chadwick discovers neutrons. Okay, we got all these kind of things being discovered. The model of the atom is up in the air. Okay, no one's really sure exactly what it looks like, right? Until Rutherford comes along. Okay, when Rutherford comes along, he establishes which model? The nuclear model. Okay, the Rutherford model is the nuclear model. Okay, and the idea of the nucleus, the kind of the basic nuclear model, has persisted since. Okay, because of his gold foil experiment where he shot the X-rays at the piece of gold foil and they went through. Some of them went through, some of them deflected. Okay, so we know that at least now the nucleus is where the protons and neutrons reside, and the electrons are surrounding it. Okay, then after that we had Bohr, who said it's like planets. That wasn't right. Okay, and after that we had de Broglie, and de Broglie's electron cloud or quantum mechanical model is the one we currently accept. You know, I have once in a while asked that as a multiple choice question. Like basically every semester I ask one guy from that list, but I mean enough to recognize him, right? I would say not enough to write a paragraph about him, right? Just enough to recognize, oh yeah, Chadwick did that, or Thompson did electrons, or whatever, right? Okay. Okay, so number 7, we discovered the atom had smaller parts, which we've discussed already several times as we've gone through this. Okay, so we've got the protons, which have what kind of charge? They are positive. Neutrons, which are neutral. Okay, and electrons, which are, okay, which two are in the nucleus? Protons and neutrons. Okay, so that's what we need to remember. Protons and neutrons are in the nucleus, electrons are on the outside. Something we haven't talked about yet, okay, and that we do need to look at is how do we figure out the number of each particle? Okay, so to get the number of protons, and you'll probably want to write this down because it wasn't part of the question, but it's something we need to cover. Okay, the number of protons is figured out simply by the atomic number. Right, so on your periodic table, there's a number with no decimals after it. That's the atomic number. Okay, for hydrogen, it's 1. Okay, for carbon, it's 6. For oxygen, it's 8. Okay, that's the number of protons in the nucleus of the atom. That number never changes. Okay, about that particular material. Okay, number of electrons, same as the number of protons in a normal atom. Okay, if it's an ion, it might be different, but it's easy to figure out. Okay, so electrons is the same. Figuring out the number of neutrons, however, is different. Okay, to figure out the number of neutrons, okay, so the number of neutrons, we take the atomic mass and we subtract the atomic number. Okay, so if I was trying to figure out the number of, let's say, a number of neutrons in, let's say lead. Okay, I was trying to do one I could do in my head, so I was picking smaller numbers, but okay, and I'm going to stick with my smaller number idea. I'm going to go with silicone here. Okay, so silicone's got an atomic number of 14 and an atomic mass of 28.09. Okay, so if I take that 28.09 and I subtract its atomic number, which is 14, I get 14.09. Can I have 0.09 neutrons? No, how many neutrons are there? 14. Simple as that. Okay, you will definitely be required to do that at some point because I always, and I will repeat that, always ask on the unit exam for you to draw me the currently accepted model of the atom, and I give you a particular element to draw. If you're going to draw that correctly, it would involve you having to show the correct number of protons, the correct number of neutrons, and the correct number of electrons. Okay, so this is something you would have to be able to do in order to answer that question and draw that atom correctly. Yes, just normal rounding. And like I said, for the most part, it's blatantly obvious. There's almost no atoms that are anywhere kind of in the middle. They're either at the very high end, so it'd be like 0.8 or higher, or they're at the very low end, be like 0.1 or lower. Yeah, there's very few that would leave any uncertainty. Okay, and I certainly wouldn't pick one on a test that would leave uncertainty. I would pick one that's obvious. No, I mean like what do we currently accept? The electron cloud. So if I'm drawing an electron cloud, I'm going to be like, I'd put all the protons and neutrons and label them, and then I would draw like a cloud, and I would draw little dashes, enough dashes to count. Yeah, it doesn't have to be like a work of art. Okay, it just has to show I know it's the electron cloud, I know where everything is, and I can calculate the right number of particles. Yeah. Okay. Is this a podcast you should go over before you test? Yeah, sometimes I do that. The elements that have no exact weights are usually ones that are very short-lived. Okay, these are, if they're outlined on my periodic table, it means that they don't exist in nature. They're only produced in a particle collider. And so they tend to be very unstable and they break down rapidly. So they don't really have time to get an accurate count of their mass. Yeah. Okay, so for number 8 here, if I have a cubic centimeter of lead and a cubic centimeter of carbon, it's not really the greatest analogy, but we're going to go with it. Okay, let's say I have this basically about the same amount of each. Why is one heavier than the other?
Because lead has 82 protons, carbon has 6.
Right. If I have the same number of carbon atoms and the same number of lead atoms, and I put them together, the lead's going to be way heavier because lead atoms are huge compared to carbon atoms. Carbon atoms only have 6 protons in the nucleus, okay, and 12 particles period in the nucleus. They're quite small compared to lead, okay, which is 82 protons, and okay, it's a much bigger atom, so there's just more matter there. Right? So it's naturally going to be heavier. Has nothing to do really with density in that case. It's more about the size of the atoms. If I had the same number of atoms of each, lead would be heavier. All right, question number 9. Nuclear reactors use atoms with very large nuclei like uranium, which has 237 particles in its nucleus, for fission, which is the splitting of the atom. Why don't they use smaller, less dangerous atoms like lithium, which only has 7 particles in its nucleus? Bigger atoms are less stable, yes.
And there's not enough energy between that small atom.
Bigger the atom, the more energy is going to be released. It's easier to hit. It's a bigger target. Okay. I mean, it's like if you're, shooting a BB gun at a pop can on a fence post or the side of a barn. Okay. The side of the barn is easier to hit usually because it's a much bigger target. All right. Okay. Number 10, atoms are indivisible. Okay, we already talked about this. We know that that's no longer true. Okay, nuclear technology has allowed us to split the atom. We know that some atoms kind of naturally break down. They're radioactive on their own. Okay, it's still somewhat true as long as there's no human technology present. Okay, the uranium that's used in nuclear reactors is a highly concentrated fuel. When you find the ore that uranium comes from in nature, okay, I mean, it's not a place you'd want to like build a house on and live over top of, but it's not nearly as radioactive as the stuff we use in nuclear reactors because it's not nearly as concentrated. Okay, they mine actually quite a bit of it in Saskatchewan. Okay? In fact, the nuclear material for the first nuclear bombs was actually mined in Saskatchewan, okay, believe it or not. So yeah, there's a fair amount of nuclear material there, but it's not concentrated. It has to be prepared and concentrated properly for the fission reaction to really occur in a huge kind of reaction way. All right, number 11, from what you know of the structure of the atom, how do you think the atom stays intact? Why do the electrons not fly off or the protons separate from the nucleus? Right, there's an electromagnetic attraction there. Okay, electrons are negative, protons are positive. Okay, so they attract each other and they kind of stay together. There's also some forces that you talk about in physics 30 called like the strong atomic force and all kinds of things like that that actually hold atoms together. But it does have to do with the electromagnetic nature of the particles themselves. Okay, to a proton, a neutron is negative because a proton is entirely positive and a neutron is neutral. By comparison, it looks negative. So they kind of stick together in there. Okay, the electrons don't fly off because they're negative and they're attracted to the nucleus, which to them looks very positive. They don't crash into it, however, because when they get too close, okay, they're moving fairly fast. And when they get close to the nucleus, again, there's these atomic forces that basically start to repel them and keep them away when they get to a certain point. Okay, it's not very nice to say, but it's like, if you're looking at something from far away and like you're questioning it, you move closer to it, and then when you get to it, you're like, oh God, and you back up. Okay, it just wasn't what you expected. Okay, kind of like that for electrons near the nucleus. Okay. All right, number 12, the same principle that makes glow-in-the-dark materials work is used by plants to produce food. How might this work? Okay, what process is that? Okay, so photosynthesis works because what happens to electrons?
Absorb energy, they start moving faster, and then when light, and when they are no longer exposed to it, they move down and disperse their energy.
Right. It has to do a bit with the law of conservation of energy. Energy can't be created or destroyed. So an electron absorbs energy, it moves faster and moves away from the nucleus. So now it has more energy. When the light is gone, that energy is also gone. So they begin to move back down. Okay, and as they fall back down towards the nucleus, they lose the energy that they had gained. That energy is captured by the chlorophyll molecules, and it's used to break apart carbon dioxide and water and make sugar. Okay, so they gain the energy, and then when they fall, they release it. That energy is harnessed, okay, in a complex chemical reaction you'll learn in biology 20, okay, that helps to make glucose. All right, questions on any of those? Okay, so make sure you keep those with you. I would say that would be your material to study for Thursday's quiz, which I will post tomorrow. Okay. All right.